The Grand Design by Stephen Hawking and Leonard Mlodinow. Picture this. You're lying on your back, gazing up at a blanket of stars, and suddenly you feel it. That delicious mix of insignificance and connection. Like you're both a tiny speck and part of something magnificent. Humans have been having this exact same moment for millennia, asking the same spine-tingling questions. Why are we here? Where did everything come from? And the big one, why is there anything at all? For most of our history, we've filled in the blanks with stories about gods and creation myths. We needed someone in charge, a cosmic director calling the shots. But then, something fascinating happened. Over the last few centuries, a completely different narrative started taking shape, written not in ancient scrolls, but in equations and experiments. This is the story of science. And when it comes to pushing this story to its absolute limits, few have done it quite like Stephen Hawking. Teaming up with Leonard Mlodinow, Hawking went after the biggest game of all, using cutting-edge physics to answer those ancient, nagging questions about existence itself. The result? A book called The Grand Design. This isn't your typical dry science textbook. It's more like an expedition to the furthest reaches of what humans know, a bold attempt to answer questions that used to belong to priests and philosophers. In fact, Hawking and Mlodinow make the audacious claim that, quote, philosophy is dead because it simply hasn't kept pace with the mind-melting discoveries of modern physics. So what is this grand design anyway? Is there a benevolent creator watching over us like some cosmic parent? Or is the truth something far weirder, far more incredible than anything our ancestors dreamed up in their wildest moments? We're about to find out. We'll journey from Newton's orderly clockwork universe to the absolutely bonkers world of quantum mechanics. We'll discover that reality might be nothing like what it appears, that the past isn't necessarily fixed, and that our universe might just be one bubble in an infinite cosmic foam. By the time we're done, you'll understand how, according to Hawking, the universe essentially created itself from absolutely nothing, why the laws of physics seem suspiciously perfect for our existence, and how we tiny, seemingly insignificant creatures have become, in a very real way, the masters of our cosmic domain. Fair warning, this story will shake up everything you thought you knew about where you fit in this wild universe of ours. Our story starts where all human stories do, with mystery. From the moment we could think at all, we've looked around at this bizarre mixture of beauty and chaos and wondered, what's going on here? Ancient people had simple, satisfying answers. Gods ran the show. The Vikings, for instance, believed that eclipses happened when two massive wolves named Skoll and Hati finally caught the sun or moon. When the sky went dark, everyone would grab pots and pans and make an unholy racket to scare the wolves away. And guess what? It worked every single time. The sun always came back. Of course, eventually someone noticed it came back, whether they made noise or not. Patterns started emerging. Eclipses weren't random wolf attacks at all. They were predictable. This was huge. It marked a revolutionary shift in how humans thought about the world. We were witnessing the birth of an idea that would change everything. The notion that nature isn't governed by the moods of gods, but by consistent, discoverable rules. This journey from a world of divine whimsy to a universe of laws started with the ancient Ionian Greeks, brilliant thinkers like Thales of Miletus. They were the first to suggest that this complex world could be understood through simple principles, no gods required. This new thinking gave birth to physics. Pythagoras supposedly discovered that the length of a musical string determined its note, following a mathematical formula. That might have been the very first piece of theoretical physics. Democritus imagined everything was made of tiny, indivisible particles he called atoms. And get this, Aristarchus figured out that Earth wasn't the center of the universe 17 centuries before Copernicus got credit for it. The guy argued that we were just another planet orbiting a much larger sun. But here's the thing. This idea of an impersonal, law-governed universe freaked people out. Where did free will fit in? What about purpose? What about the gods? It suggested we weren't special at all. This human-centered view was so powerful that the Ionian ideas basically got shelved for nearly 2,000 years, gathering dust until folks like Galileo dusted them off again. For centuries, the world was seen as God's personal playground, where the rules could be bent or broken at will. In 1277, a bishop in Paris, acting on papal orders, actually condemned the idea that nature follows laws because it seemed to limit God's power. Ironically, that same pope died a few months later when his palace roof collapsed on him. Even he couldn't escape the law of gravity. It wasn't until the 17th century, with thinkers like René Descartes and especially Isaac Newton, that the modern concept of scientific law really took off. Newton's laws of motion and gravity were a game-changer. A few elegant equations could describe everything from a falling apple to planets orbiting the sun. The universe seemed like a grand, predictable machine. Later, the scientist Laplace took this to its logical extreme with his idea of scientific determinism. He believed that if you knew the complete state of the universe at any given moment, you could predict its entire future and reconstruct its entire past. When Napoleon asked where God fit into this picture, Laplace famously replied, "Sire, I have not needed that hypothesis." This clockwork universe felt right. It matched our everyday experience. Objects have definite positions and follow predictable paths. But as technology improved, and we started peering into the atom, we discovered something unsettling. This classical picture couldn't explain what we were seeing. Nature, at its smallest scales, doesn't play by the rules we're used to. It plays by quantum rules. And this is where things get really weird. To wrap your head around this new reality, Hawking asks us to consider an oddly specific example. A few years ago, the City Council of Monza, Italy, banned keeping goldfish in curved bowls. Their reasoning? The curved glass gives the fish a distorted view of reality, which they deemed cruel. But wait, how do we know we have the true, undistorted picture of reality? Maybe we're all swimming in some giant cosmic goldfish bowl ourselves, our vision warped by forces we can't even perceive. Here's the thing. The goldfish's view of the world is different from ours, but is it any less real? From inside its bowl, a person walking in a straight line would appear to move in a curve, but that goldfish could still create scientific laws from its distorted perspective. Those laws would be more complicated than ours, sure, but they'd work. They'd let the goldfish predict how objects outside its bowl would move. If a goldfish scientist came up with such a theory, we'd have to admit its view is a valid picture of reality. This brings us to a central concept in the grand design: model-dependent realism. The basic idea is there's no such thing as a picture or theory-independent concept of reality. Our brains constantly build models of the world based on what our senses tell us. When a model successfully explains what we observe, we give it the stamp of reality or absolute truth. Consider the famous debate between Ptolemy and Copernicus. For 400 years, the Ptolemaic model, with Earth at the center, was accepted reality. It was complicated, with planets moving in circles upon circles, but it matched observations. Then, Copernicus proposed a simpler model, with the sun at the center. We often say Copernicus proved Ptolemy wrong, but that's not quite accurate. You can use either model to describe what you see in the sky. The real advantage of Copernicus's system? The math is way simpler. According to model-dependent realism, asking whether a model is real is pointless. The only meaningful question is whether it matches observations. If two different models both work, like our view and the goldfish's view, you can't say one is more real than the other. You're free to use whichever is more convenient. This framework is essential because modern physics is about to take us somewhere that completely defies common sense. It's a world where our classical, intuitive model of reality simply falls apart. To see just how bizarre this new world is, let's look at what physicist Richard Feynman called the experiment that contains all the mystery of quantum mechanics. It's the double-slit experiment. Imagine you're kicking soccer balls at a wall with two vertical slits in it. Behind the wall is a long net to catch the balls. Most balls hit the wall, but some go through one slit or the other. You'd expect to see two distinct clusters of balls in the net, one behind each slit. If you close one slit, that cluster disappears, but it doesn't affect the other one. Open it again, and the total number of balls at any point just increases. The pattern with both slits open is simply the sum of the two individual patterns. This is everyday, common-sense reality. But that's not what happens when you shrink the experiment down to the molecular world. In 1999, physicists in Austria did this with tiny soccer ball-shaped molecules called buckyballs. The results were mind-blowing. When both slits were open, the buckyballs didn't form two simple clusters. Instead, they created an interference pattern, a series of bright and dark bands, exactly like what you'd see if waves of water passed through the slits and interfered with each other. Here's the kicker. There were spots where fewer molecules landed when the second slit was opened. Let that sink in. Opening a second path somehow prevented molecules from reaching places they would have otherwise reached. How is that even possible? It's as if each tiny molecule, traveling all by itself, somehow knows whether both slits are open. It's as if it goes through both slits simultaneously. This wave-particle duality is foundational to quantum mechanics. Tiny objects, like electrons, buckyballs, and even light itself, can act as either a particle or a wave, depending on how you observe them. This bizarre behavior led Richard Feynman to a radical insight in the 1940s. He asked, how does a single particle create this interference pattern? Classical physics says a particle must follow one single path from source to screen. But Feynman's idea was radically different. He said the particle doesn't take one path. It takes every possible path, all at the same time. A particle traveling from point A to point B doesn't just go through the left slit or the right slit. It also takes paths that loop through the left, out the right, and back through the left. It takes paths that detour to the nearest restaurant, circle Jupiter a few times, and then head to the screen. This concept is called the Feynman sum over histories, or alternative histories. In this view, the interference pattern makes perfect sense. The paths going through one slit interfere with paths going through the other, creating those bands of light and dark. It sounds like pure science fiction, but this mathematical framework perfectly reproduces all the laws of quantum physics. For large objects like actual soccer balls, all the weird, loopy paths cancel each other out, leaving only the straight, classical path predicted by Newton's laws. That's why we don't see quantum weirdness in everyday life. But on the subatomic level, this multiverse of paths is reality. This idea has a staggering implication that completely shatters our classical worldview. It concerns the nature of the past itself. In our everyday world, the past is a definite series of events. If a vase lies broken on the floor, we can trace back the single history that led to it. But quantum physics says this isn't true. The unobserved past, just like the future, is indefinite and exists only as a spectrum of possibilities. The universe doesn't have a single past or single history. And here's the strangest part. Our observations in the present can actually affect this indefinite past. Physicist John Wheeler proposed a delayed choice experiment to illustrate this. It's like the double-slit experiment, but you wait until the very last moment, just before the particle hits the screen, to decide whether you're going to measure which path it took. When you do this, the results stay the same. If you choose to look, the interference pattern disappears. If you don't, it appears. But think about what this means. The particle passed the slits long before you made your choice. Your decision in the present seems to have reached back in time and influenced what the particle did at the slits. Wheeler even imagined a cosmic version, where light from a distant quasar, billions of light-years away, is bent by an intervening galaxy, creating two paths to Earth. Our choice of how to observe that light today could affect the path it took billions of years ago, before Earth even existed. The conclusion is inescapable. We create history by our observation, rather than history creating us. This brings us to the biggest question of all. If we can apply this quantum logic to a single particle, can we apply it to the entire universe? Hawking and Mlodinow say absolutely. Just like a particle, the universe doesn't have a single, unique history. It has every possible history, each with its own probability, all existing simultaneously in quantum superposition. This idea unlocks the mystery of the origin of everything. The classical Big Bang theory, based on Einstein's general relativity, tells us the universe began from a point of infinite density and temperature, a singularity. But at that point the theory breaks down. It can't describe the actual moment of creation. But if the origin of the universe was a quantum event, we must apply the sum over histories to the universe itself. What does this mean? It means the universe didn't start in one specific way. It started in every possible way. Hawking offers a beautiful analogy. The beginning of the universe is like the South Pole of Earth. If you think of latitude as time, then as you move north from the South Pole, the circles of latitude get bigger, just like the universe expanding. The universe starts as a point at the South Pole, but the South Pole is just like any other point on the globe. There's no edge, no boundary. Asking what happened before the Big Bang is like asking what's south of the South Pole. The question is meaningless. This is called the no-boundary condition. When you apply Feynman's sum over histories with this no-boundary condition, a startling picture emerges. The universe appeared spontaneously, creating itself from nothing. And this isn't just one universe. The sum includes histories for countless other universes, most of them wildly different from ours. Welcome to the multiverse. Think of it like bubbles forming in boiling water. Many tiny bubble universes pop into existence and vanish almost immediately. But a few grow large enough to survive, expanding at an ever-increasing rate. These are universes that undergo rapid inflation. Our universe is one of those successful bubbles. Now we're getting close to the ultimate question. Why is our universe the way it is? Why do the laws of nature, the strength of gravity, the charge of an electron, have these very specific values? Turns out, our existence is balanced on a knife's edge. The laws of nature seem incredibly, almost miraculously fine-tuned to allow for life. For instance, carbon, the basis of all life we know, is created inside stars through something called the triple alpha process, where 3 helium nuclei fuse together. Fred Hoyle, the physicist who figured this out, realized that for this to happen at a rate sufficient to create the carbon in the universe, the laws of nuclear physics had to be exquisitely tuned. If you change the strength of the strong nuclear force by as little as 0.5%, or the electric force by just 4%, you'd destroy nearly all the carbon or oxygen in every star. Life as we know it would be impossible. It's not just one or two constants either. Dozens of values in physics seem perfectly calibrated. If the proton were just 0.2% heavier, it would decay, and atoms wouldn't be stable. If there were 4 large space dimensions, instead of 3, planetary orbits would be unstable. Planets would either spiral into their sun, or fly off into the cold darkness of space. Either way, life wouldn't have the stable environment it needs to evolve. So what do we make of this apparent miracle? This is the strong anthropic principle. The fact that we're here to ask the question constrains what laws of nature we can observe. For many people, this fine-tuning is the ultimate proof of a benevolent creator, a God who designed the universe specifically for us. But modern physics offers another explanation, one that doesn't require a designer: the multiverse. If our universe is just one among a vast number of others, each with different physical laws, then fine-tuning becomes not a miracle but a statistical certainty. Imagine a gigantic clothing store with endless racks of shirts. Most won't fit you. They'll be too big, too small, or have sleeves for an octopus. But if the store is large enough, you're guaranteed to find one shirt that fits perfectly. Our universe is that perfect shirt. We find ourselves in a universe that allows our existence because we simply couldn't exist in any of the others. Our presence selects this particular universe from the vast landscape of possibilities. This brings us to the final piece of the puzzle, the theory that allows for this multiverse of possibilities. For decades, physicists have been searching for a single unified theory of everything, a theory uniting all four forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. The best candidate we have is M-theory. M-theory isn't a theory in the usual sense. It's more like a network of different theories, each describing reality in different situations, like a collection of overlapping maps for the whole Earth. M-theory predicts a universe of 11 dimensions, 10 of space and 1 of time. We only experience 3 space dimensions because the other 7 are curled up into such a tiny space we can never perceive them. The precise way these extra dimensions are curled determines the apparent laws of nature and the values of physical constants in that particular universe. And here's the crucial part. M-theory doesn't predict just one way for them to curl. It allows for a colossal number of possibilities, perhaps as many as 10 to the power of 500. That's a 1 followed by 500 zeros. Each possibility corresponds to a different universe with its own unique set of laws. This is the grand design. Not a single unique universe created by God, but a vast multiverse generated spontaneously by the laws of physics. So let's circle back to our original questions. Why is there something rather than nothing? Because of gravity. The authors explain that the total energy of the universe must be 0. Matter has positive energy, but gravity is an attractive force, meaning it has negative energy. The negative energy of gravity perfectly balances the positive energy of matter. On the scale of the entire universe, the books balance. Because of this, the universe, can and will create itself from nothing. No divine spark needed. Spontaneous creation is the reason the universe exists. Why do we exist? We exist because in the vast landscape of the multiverse, a universe with our specific set of fine-tuned laws was bound to arise. And in that universe, tiny quantum fluctuations from the very beginning grew into the galaxies, stars, and planets that eventually led to us. And why this particular set of laws and not some other? Because these are the laws operating in the universe we happen to inhabit. By observing them, we're simply selecting our own history from the sum of all possible histories. In the end, Hawking and Mlodinow present a universe that's both deeply humbling and incredibly empowering. We're not the center of a tailor-made creation. We're products of quantum chance, inhabitants of one of a vast multitude of worlds. And yet, the fact that we, mere collections of fundamental particles, have been able to come this close to understanding the laws governing us and our universe is, as they say, a great triumph. We've looked into the abyss of reality and found not the hand of a creator, but the elegant, impersonal, and absolutely awe-inspiring workings of physical law. We've found the grand design. When you close a book like the grand design, it's hard not to feel like your perspective has fundamentally shifted. It takes the biggest questions humanity has ever asked and provides answers that are both intellectually satisfying and emotionally challenging. For centuries, the idea of a grand design was inseparable from the idea of a grand designer. The intricate order of the cosmos, the perfect conditions for life on Earth, all of this seemed to point toward deliberate, intelligent creation. What Hawking and Mlodinow have done is brilliantly subversive. They've hijacked the term grand design to mean something entirely different. A universe that designs and creates itself through fundamental laws of nature. The most powerful and perhaps most difficult idea in the book is that our human intuition is a terrible guide to ultimate reality. Our brains evolved to help us survive on the African savanna, to throw spears and avoid predators. They didn't evolve to comprehend quantum mechanics or cosmology. Concepts like the multiverse, sum over histories, or time behaving like a dimension of space feel alien and strange because they operate in a realm far beyond our everyday experience. The book asks us to trust the mathematics and observations, even when they lead to conclusions that defy common sense. It's a call to intellectual humility. At the same time, there's profound wonder in this worldview. The idea that we're the product of random quantum fluctuations in the early universe is, in its own way, as magical as any creation myth. It connects us directly to the birth of the cosmos. The atoms in our bodies were forged in the hearts of stars that exploded billions of years ago, a process made possible by the very fine-tuning of physical laws the book explores. We are, quite literally, stardust. So how can we apply these grand cosmic ideas to our own lives? It might seem impossible, but there are a few simple takeaways. First, embrace curiosity. The entire history of science is a testament to the power of asking why. Don't accept things as they are. Question them. Learn about them. The universe is far stranger and more wonderful than we can imagine, and the joy of discovery is one of the greatest experiences available to us. Second, appreciate the improbability of your existence. Whether you believe the fine-tuning is God's work or the result of a cosmic lottery in the multiverse, one fact remains. The conditions allowing for your life are astonishingly rare. Take a moment to appreciate that. The air you breathe, the water you drink, the planet you live on, it's all the product of an incredible series of cosmic coincidences. This fosters gratitude and responsibility to make the most of this fleeting, precious opportunity to be alive and aware. Finally, think in terms of models. Remember the goldfish bowl. The book teaches us that our perception of reality is just that, a perception, a model built by our brains. This is true, not just in physics, but in daily life. The reality of our social circles, our careers, our own limitations. These are often just models we've built, and models can be changed. Understanding that there isn't one single absolute truth gives you freedom to question your assumptions and build new, more useful models for your life. That was our journey through the Grand Design by Stephen Hawking and Leonard Mlodinow. We've touched on the deepest questions of existence, but here's the truth. A summary can only ever be a map. The real treasure is exploring the territory yourself. The book itself contains the full depth of the stories, the analogies, and the sheer intellectual beauty of the arguments. This summary is here to help you decide if this is a journey you want to take. If anything we've discussed has sparked your curiosity or challenged your perspective, I urge you to pick up a copy. Reading it isn't just about learning facts. It's about fundamentally changing how you see your place in the universe. A link to the book is in the description. Also, if you found this summary valuable and want to continue exploring ideas from the world's most influential books, please take a moment to like this video and subscribe to the channel. It lets us know we're on the right track and ensures you won't miss our next adventure. Let's keep learning and growing together.